Hello, everyone. This week, our lab will be on temperature, which is something that I think all of us have a really good understanding of, to begin with. But it's important to understand the physics behind because we're going to build on con concepts from temperature on other units in this semester. So, like temperature is really important for determining how clouds form, how rocks form, which way ocean currents flow. So many things that on the physical processes on this earth are governed by temperature first. So up here on the screen, there's three portraits of older gentlemen. You actually should already know the names of these people already. They are famous for their scales of temperature, which they came up with: Fahrenheit, Celsius, and Lord Kelvin. I'm gonna throw out one more here, which you may or may not be familiar with. This is Sean Paul, known for his temperature songs, 2005 smash hit. But the first three guys, they had a much bigger impact on temperature concepts than Sean Paul. But um, let's start off with just a mini physics lecture. Starting off with like thermal energy. Energy is just means the ability to do something that could be raise the temperature a degree, or there's so many other kinds of energy too that I'm just not even going to mention. Um, and of course, the first law of thermodynamics, if you don't know, states that energy cannot be created or destroyed, only transforms. The point here is that how this relates to temperature is that um, temperature is really the average kinetic energy of the atomic particles in a box, or in a section of anything, matter. But that temperature represents that average kinetic energy. So when heat flows, so things go from hot and they cool down by giving off that thermal energy. That the point there is that energy is not created or destroyed, it's only transformed or moved around. So we have, of course, very familiar with the ways to measure temperature. There's Fahrenheit and Celsius. Here in America, we use Fahrenheit for whatever reason, but they are measuring the same thing. It's average kinetic energy of the molecular motion, or motion of very, very small particles that are always moving around and bumping into each other. And in Celsius, it's easy to remember what temperature water freezes and boils. It's 0 and 100. Versus in Fahrenheit, water freezes, of course, at 32 and boils at 212. In lab today, we're going to ask you just a couple questions just to make you do a little math. You're just converting Fahrenheit to Celsius and back again. Those formula are in the lab document, so don't need to write these down here. Now, on the first slide, I said that, well, Kelvin also invented a temperature scale, which is true. It's related to Celsius in that it has the same steps of degree, but Kelvin actually is a better representation of the molecular motion of particles. So when Kelvin were to go to 0, it would be negative 273 degrees Celsius. So it's just unbelievably cold. At that point, molecular motion stops. And as you increase temperature, there's more molecular motion. Okay, so that lines up with what we've already said. Now, to relate this to heat, which you should not conflate the two terms, but they're related. Heat, to illustrate what I'm going to say, try to, if you're standing on if there's something metal nearby to you, touch something metal with one hand and touch something plastic or wood, or even like a pillow with your other hand. Now, if these two things were both sitting in your room for enough time, we can assume that they have the exact same temperature. But you might already know that the metal is going to feel colder. And why is that? This has to do with the conductivity. Metal is a better conductor than, say, plastic or wood, but we can relate this to a term called sensible heat, or heat that we can sense. So the metal thing that you were touching would pull thermal energy out of your hand faster than the non-conductive property would. So that's sensible heat. These would both have the same temperature. The metal thing might heat up a little quicker just because it can better pull that thermal energy away from you. But keep that in your mind as we go forward. So heat is really the transfer of thermal energy. And this, just quick diagram, I'm not going to go over everything, but be able to recognize that there are different ways that you can move around heat, transfer heat. And pretty much all of these happen on our planet, either deep in the ground or in the atmosphere or in oceans and lakes and rivers. Radiation, of course, coming from the sun, that's a huge one. We're going to talk a lot about that one today. So conduction, convection, advection, these are ways to transfer energy, which is moving heat. Now, radiation, we're going to talk the most about that one today, because any physical geography class has to start here, that all of our energy comes from the sun. Now you might say, oh, well, we pull up fossil fuels and we burn those, or we use other forms of energy. Well, for 99.9999999% of all time, all of the energy that sustains ecosystems and heats the atmosphere, heats ocean, that's coming from the sun. Some of that might come from like thermal vents or volcanoes, geothermal energy, but radiation is where we get most of the energy in our system, if we call the entire Earth a system. And it is, because the atmosphere is always mixing around. Any gas particles at one point in the atmosphere could be on the other side of the world, or any other place in not that long of a time. So the atmosphere is always mixing around. And the insolation is just a vocabulary term that means the incoming solar radiation. It's pretty easy to remember when you break it down here. So incoming solar radiation. Now, at the top of the atmosphere, the insolation is going to be not impacted by anything else. There's just basically empty space between the sun and the top of the atmosphere. So this top image here on the top right, that basically just shows the watts per square meter, or amount of power from the sun that's coming, or energy. So the most energy hits near the equator, and that's just related to the angle. So if it's hitting straight on, then it's going to be the most intense, versus if the angle here of insolation hitting the top of atmosphere is more oblique, or it's a smaller angle, then there's going to just be less. That's just plain old trigonometry. But this bottom right image shows the amount of insolation that reaches the surface of the Earth, and that varies a little bit due to things like particles in the atmosphere itself, wind currents, a lot of things. But understand that at the top of the atmosphere, insolation is all pretty much equal, but it depends on your latitude. And what actually is that radiation? It's a mixture, a whole spectrum of different wavelengths of photons. Here's more physics, but you really don't need to know that much. Basically, if know that the visible light that we can see, some of that comes from the sun, of course. If you look at the sun, it's super bright. Invisible light, but not only visible light, but also UV. the stuff that would give you a sunburn. Or infrared, those are longer wavelengths, and that's what really gives you that warm feeling if you go stand out in the sun. And there are also others like X-ray, gamma rays, which thankfully mostly get hung up in the upper atmosphere, and microwave and radio wave, which are coming from, so many things. A lot of radio waves comes from the Earth itself, um, uh, but those X-ray and gamma rays, for example, that I was talking about on the previous slide, thankfully get hung up in the upper atmosphere, meaning they interact with the gas way up in the highest parts of the atmosphere, like in the thermosphere, and interact with those gas particles up there and get absorbed and converted into thermal energy. So they increase the motion around. Because X-ray and gamma rays are really high energy. They would just absolutely fry us if we didn't have this atmosphere acting as a window, which really means that the atmosphere allows some wavelengths from the sun to pass through very easily, like radio waves and visible waves, but it acts as a partial filter for others, like UV radiation, which interacts very well with ozone, which is a layer, it's a gas that is very common in the upper stratosphere, which is where most of the UV light gets filtered out before it even reaches the surface. Now, there's still enough UV radiation to give people, skin cancer and such, but it would be much worse if you were to go up into above the stratosphere and then stick your hand out. You would get fried pretty quickly. You would have other problems too. But so the point here is that radiation is a spectrum, meaning there's different wavelengths that come in. Some of those we're able to see and feel, but not all of it reaches the ground. The stuff that does reach the ground, the radiation that does reach the ground, some of that then is reflected back up, and that we will call albedo. And some of that, most of it, is absorbed by the surface of the ground. The roof of our house, the ground outside, mountains, oceans, etc. Everything on the surface absorbs some radiation. And that now we need to differentiate just a little bit further the types of radiation. So we've already mentioned every part of the spectrum, the electromagnetic spectrum, and that the short wave radiation is the stuff like UV or X-ray gamma or even visible. And this is just something we're not going to get into, but basically anything in the universe with high enough temperature emits some long wave radiation. So relatively speaking, the Earth is actually pretty warm, especially when it gets heated up by that incoming shortwave radiation from the sun. So the ground is heating up. It's high noon in Arizona, and the ground is like 140 degrees. So that ground itself is going to emit radiation too. And that phenomenon is actually what keeps the air nice and warm near the surface. This is actually what warms the lower atmosphere, like where we're hanging out right now. We're in the lowest parts of the troposphere, and we can thank most of our heat that we feel in the lower atmosphere, the air temperatures, thanks to that long wave radiation going back up from the surface and heating what was, nearest to the ground first. So it makes sense that as you go up, you increase altitude throughout the troposphere, which is just the lowest part of the atmosphere, then temperature would go down because you're further away from the source of heat, which is actually that long wave radiation from the ground. Now, this is a little counterintuitive. You wouldn't think of the air being heated up by the ground. That might not be your first thought, because when you step outside on a sunny day, your body absorbs that shortwave radiation. But you have to also think that your body is also giving off heat the whole time to the air around it, if the air is, less than 98 or whatever degrees. So this, so now let's understand better that we know that as generally as you go up throughout the atmosphere, temperature decreases, which is true for everywhere that we're going to be hanging out or taking a plane in, which is the troposphere and the lowest parts of the stratosphere, maybe. But that does not continue all the way up into space. The temperature, if you look here on the right, there's a warm patch, a higher temperatures actually in the top of the stratosphere. And that's due to the ozone layer. Because, like I already said, the ozone gas, O3 gas, interacts with that incoming shortwave radiation really well. So say UV light might hit an ozone molecule and it causes it to move faster, which increases the kinetic motion of that particle, which thus increases its temperature. Now, the gas is also very spread out. It's very low density. If you cannot breathe this high up in the atmosphere, because the air pressure is so low. So that means that you might not be able to feel really warm because there's very little sensible heat. There's not much transfer from actual matter to other matter, but that radiation goes through really easy. Now, above the stratosphere, and just FYI, at the top of any of the sections of the atmosphere, we just add a pause suffix to the end of that word. So the top of the troposphere is tropopause. Top of the mesosphere is mesopause, etc. So above the stratopause, we have another separate layer called the mesosphere of the atmosphere. There, you can think of that as like pretty middle, medium. Not much interesting is happening. Like not anything that unique, because as you go up through the mesosphere, temperature continues to decrease. As you get up into the thermosphere, where that really high energy radiation starts to interact with the first little bits of gas that are up there, then we have phenomenon like aurora lights or crazy high temperatures in the thermosphere, even though that gas is super spread out because it has that really high energy shortwave radiation coming in and interacting with it. And that thermosphere acts like a window and is closed to most of that shortwave radiation, which is good for us because, that X-ray and gamma rays are super damaging to DNA and a lot of things. So the thermosphere, as the name implies, it has really high temperatures, but the density of particles is very low. It's basically almost space. And then as you go down, then there's the mesosphere, then stratosphere, which includes the ozone layer, and finally, and most interesting, the troposphere, which includes all of the weather that we're going to experience. The top might be, where you would fly in a plane. Everything interesting happening on, for life is happening in the troposphere. So here's just reiterating that don't be confused by these terms tropopause or stratopause. It just means the very top of the layer. And in reality, there's not one clear-cut, invisible line that denotes it. It's determined based on the physical properties that we measured. So let's decompress from all this heavy physics. Let's look a little bit at some of the extremes of temperature that you can have on Earth. Now, like I already said, the surface of the ground is could be a lot hotter than the air because it's the surface itself being so warm that actually heats up the air around it or above it. So, the hottest surface temperature ever recorded was actually 159 degrees Fahrenheit, which is just bonkers. They actually didn't know where in the Lut Desert in Iran, it's very desolate and it's very hostile. They don't have very many weather stations. It wasn't until scientists were able to use satellites to and measure the surface temperature with that to actually know that this place in Iran has the highest surface temperature in the world. Before then, it was like 156 or something, so it was still pretty hot. But um, the hottest air temperature. Now to do that, they rely on weather stations, which are standardized. You have to have a thermometer in the shade. They have two thermometers actually at any given moment, and they have digital and mercury and alcohol too. But people have measured almost 130 degrees last year in August in Death Valley, California. And there are many other close ties with that. Not, Death Valley is known for being the hottest air temperature, but there are many other desert places that are really low elevation that also have temperatures comparable. And the coldest air temperature, I think there's got to be colder temperatures out there, but this is cold enough. 128 degrees negative Fahrenheit in Antarctica. That's too cold. And I'm from Wisconsin, born and raised, but so I'm able to tolerate anything up to or down to like negative 30, 35 maybe. This is just that's inhospitable to human life. Okay, and now let's look at um this is shifting gears a bit, but obviously, temperatures are cold at night and they're warm during the day. But you can break that down even further. You can say the hottest temperature of the day is usually in the early afternoon, between like 2 p.m. to 3 p.m. And the coldest part of the day is not at midnight, but rather just before dawn. So depending on when sun rises, that might be 4 a.m., 5 a.m. You get the point. And why is that? You would you would think, right? Your first gut reaction might be when the sun is highest in the sky, then the radiation would be most intense, right? As the sun gets lower, remember that solar angle gets smaller, so radiation is less. Don't worry about that too much, but um, it's not. It's actually this is related to that long wave radiation effect that I was talking about. So remember, the air temperatures in the troposphere that we rely on, we like it nice and warm, especially this time of the year. We want that heat, and that comes from the ground that was heated up by the sun. Every day it gets heated up by the sun and it cools off throughout night. So all through the morning, the surface of the ground, but that also includes things like water or buildings, um, anything on the surface would heat up during the day because it absorbs the incoming solar radiation from the sun, and then it re-emits long wave radiation to heat up the lowest parts of the atmosphere. And so there's a lag effect, right? So all the morning, the surface temperature is increasing, and then when it's at its peak, then it gives off the most heat, and it takes a little bit, a little time for the atmosphere to catch up, as it were. So there's a lag effect. The atmosphere lags behind the surface temperatures, and if you apply the inverse logic to that, then the coldest part of the day is just before the dawn because all throughout the night, the uh, ground and surface was giving off all of the long wave radiation that it can, and it starts to cool down to its lowest point just before sunrise. Okay, so I know I went through a ton of material just there, but this basically everything I just said is going to be on the lab document. So if you might want to rely a little bit on what I'm saying because you're going to have to explain the lag effect. Okay, so that's all the information you need for this lab. This lab is I think it should be pretty quick for most people. Um, we ask you to watch the video of me doing the at-home experiment, which it's just going to be extra credit if you do it yourself. But there are 3 required questions that everybody has to answer that you can just watch my video and you'll see the gist. Basically, you put a couple drops of food coloring into water at different temperatures when the water is just perfectly still and see how fast it mixes. Because this is getting at that kinetic motion of particles. As particles move around faster, they're able to mix faster. That's related to diffusion. That video is up on Canvas and also in the lab document, and as well as an Excel file, a .xlsx file, which you will need. It just has like 6 rows of data that you're going to have to just make a quick graph, a line graph, or just a scatter graph with dots. You can do it on the computer. You could even draw it out. It doesn't have to be pretty. It has temperature values at different points in the atmosphere. So this is going back to the temperature profile of the atmosphere. So it shouldn't just be one straight line. There should be a couple peaks in there. And then finally, it's just talking about lag effect. So if you have any questions, feel free to reach out to me, of course. Best of luck.